Okay, today we will learn about Chapter 3, Vector Spaces. There are 6 sections in this chapter. We first learn Section 1, Definition and Examples. In this section, we first learn simple examples. So we say vector spaces or we say linear spaces. It should satisfy 3 conditions. First one, a set of elements on which the operations of addition and scalar multiplication are defined. Second, operations satisfy closure property. The operations including the addition and the scalar multiplication. And thirdly, the set together with the operations, addition and scalar multiplication forms a vector space if and only if a set of axioms are satisfied. We first see some examples in R2. Okay, given you a non-zero vector in 2-dimensional real vector space, so we can write X just as X1, X2 as its 2 components, and you can draw in the figure here. So from 0, 0 point, you draw this arrow, this vector. So X are just represented by its coordinates, X1, X2 here. So X1, in fact, is a projection of this vector on the X1 axis. And similarly, X2, this coordinate is just the projection of this vector X onto the X2 axis. Okay, and here, you can draw this vector from the origin, 0, 0 point, and also you can start from any other point in this 2-dimensional space. Okay, for example, you start from A, B, from this point. Then the vector X is parallel to this X, and the coordinate of the endpoint of X is A plus X1 and B plus X2 for the second component. And the Euclidean length of X is defined in this way, just as square root of X1 power 2 plus X2 power 2. So here is the length of this vector. And for 2-dimensional vector, we know that given you any scalar alpha, alpha times X just equals alpha times this 2-dimensional column vector. So its first component becomes alpha times X1. Its second component is alpha times X2. And here, if alpha you choose, for example, -1, you will get minus X. So the original vector X, the new vector minus X, these 2 vectors, the directions are opposite. However, their lengths are same. They have the same length, but the direction are opposite. Okay, and here is 3 times X, so alpha equals 3. So this vector, the direction is the same as the original vector X, and the length is 3 times. Okay, and here this vector is -2 times X, so you choose alpha equals -2. So because you have negative sign, so its direction is opposite with respect to X, and the length is 2 times of it. Okay, and in R2, we also can compute the sum of 2 vectors, U plus V. U plus V you can just write as the addition of its components respectively. You do the summation, so you get U1 plus V1 for the first component and U2 plus V2 for the second component. So if you see in the figure here is the vector U, and here is the vector V. So the vector V start from the endpoint of the vector U, and then you can get U plus V, this new vector here, start from the starting point of U and end at the ending point of V. So this is U plus V. And here, if you draw in this figure, if here is U, here is V, then this line, this vector, this is Z, which equals U plus V. And also, if we write here this vector as W, start from the endpoint of U and end at the endpoint of V, then we know that U plus W equals V, or we can say that W equals just V minus U. Okay. And now we can see vectors in three-dimensional real vector space. And here, given you any vector in R3, you will have coordinates here, x1, x2, x3. So similarly, x1 should be the projection of x first onto the plane x1 or x2 plane, and then do the projection again on x1 axis. So this is x1. Similarly, you can get x2 and x3. And here, similarly, given you a vector x, given you a vector y, if we want to know new vector x plus y, then you just draw x here, and from its endpoint, you draw y, and then you connecting the start point of x and the end point of y, you will get x plus y. Very similar, right, to the R2 space. And of course, for general n-dimensional vector space, for any x, y in Rn and any scalar alpha, you can compute alpha times x, the scalar multiplication, which equals this new vector. Each component is alpha times xi respectively, from alpha times x1, alpha times x2 till alpha times xn. And for any two vectors x, y in Rn, its addition x plus y just equals this new vector. Its component is just x1 plus y1, x2 plus y2 till xn plus yn. So the summation of components respectively. And now we consider vector spaces for n by n matrices, real matrices space. Okay, let Rn by n denote the set of all n by n matrices with real entries. So if A represented in this way, its representative entry is Aij, and B equals Bij is representative entry, and alpha is a scalar, then we know that alpha times A, this new matrix, let us denote it as C, which equals Cij as its representative entry, where Cij just equals alpha times Aij. And the sum A plus B is defined to be A plus B equals the new matrix C, with its representative entry Cij, small cij, where Cij just equals Aij plus Bij. So you do the summation of corresponding entries in A and B.